today's video, we're going to talking about minimax algorithms using alpha beta pruning. So I assume you already understand what is minimax algorithms. If not, I will give you a roughly overview, but I suggest you to watch the link I put in the description. Watch that one first and then you come back to this one. So imagine we're writing a piece of code for a chess game. So there are two players, player one and player two. So the player one, he's trying to maximizing the chess pieces for himself on the left on the chessboard. So for player two, he's trying to minimize the chess pieces left on the chessboard for the player one. So we can represent that situation in this binary tree. So A is represent the initial state for the player one. He is trying to start. He already finished his moves. Now it's player two's turn. So assume like he only has two moves to choose. This is just an assumption, okay? And there can be many, but this is just an assumption for simplicity. So there after player two's move, there will be player one's move again. So on and so forth. So in the end, we have these green lines, green grades, which is represent the final state of the player one, how many pieces left for him on his side. So in this program, what we're trying to do is both player one and player two, they're trying their best, and what's the best result for the player one, like how many pieces the most could be left on the chessboard. That's what this program is trying to do. When I'm saying they're trying their best, what I mean is player one, he's to make the best decision to maximize the left pieces on the chessboard, and player two, he's trying to minimize the left pieces for player one, and using this as a principle to make the best move. So now we take a look at the code. Well, we're using Python as an example, but you can look at C++ or Java. They're basically the same thing, and the idea is the same, like just some minor grammar changes. So these values, we're using this value array to store the final results for the player one, like how many pieces left on his side. So this is what this array means, this value thing. And then first of all, for node A, because this is his first move, so we're calling this function. So this function has a parameter depth, which represent the depth of this binary tree, which start from 0, and we have this node index. Notice this node index is talking about this array. For example, you can thinking about there's a pointer right here, and then this node is start from this node 3. It's not a node from this trees, okay? And this maximizing player is talking about whether this node is in the maximum layer or it's in the minimizing layer. And this value basically is just this array. And we have another value for each node. It's alpha and beta. I will explain how it works in a moment later. So first of all, we will check whether we already reach the base layer or not. So if not, we'll keep going. We're gonna check whether it's a maximizing node or it's a minimizing node. So if it's a maximizing node, we'll go through its child. And notice when we execute it from this line, for example, for node A, the code is being executed till here, and then this line will calling himself again. This is called recursive call, calling this function again. So from here to here, this B node, he will re-execute this code from line 58, and then he will go through this code again. Okay, he first check whether it's in the depth node or not. If it's not, I'm going to check. Okay, right now for node B, he's not a maximum player because he's in the minimum layer. So because you remember this parameters it's set it as false. So here this one will be false. So it will go into this part. So for this part, and for the B node for this part, he will going to keep checking his left and right child, and when it's executed to this line, the same thing, like this function is gonna calling himself again to check the subchild situation. I wrote all this down on the paper already. I will show you in a second, but first of all, you need to understand these three lines. You need to keep these three lines in mind. How and also like how this program mainly structured. This is very important. You need if you can open up this. Actually, the code is here. You can open up the code. You can choose C++ or Java or whatever. You can open this page up while looking at my video at the same time, and I will go through this code line by line, and I will let you see how this program really works. So I draw everything down. You can see this graph as a huge binary tree. It's the same thing as what's showing in this website. It's just the same stuff. You can interpret this as the same thing. So like this is the part of A node, and this is the B node, and D node, and the leaves like this, and then this is the E node. It's somewhere around here, and the left and right, and this is the C node. I didn't even write it. We will see that later. But first of all, you need to understand when we execute from A node, when we're going through this first for loop, we have executed this line, which is the recursive call calling himself again, and we'll start another instance from here. These three lines won't be executed until we will have something returned to this var, and then we can execute these three lines. This is very important to understand. So later on, it's the same thing. Each time we're hitting a line of this, or calling himself again, this part won't be executed until something has been returned from the bottom, and then we can execute these three lines. So for the A, B, so the program start from A, and then executed this line, and then go from here, executed this line, and then go from here until it's hitting the bottom. It will start the final layer instance. We will have reached the leaf node. We will have some value which is 3, so it's this one. So we go from here to here, and then to here we have this 3, and then we will return this value back to D. So when we back to D, and then we can execute it. We will have this number 3, so we can execute this 3 line. So notice we have some variables best and alpha. So we have two variables, best and alpha. So this best, you can imagine this variable as vertically what's the best solution from the subchild, and what's the best solution can be returned to this node currently. So right now, this D node, he has finished checking this left side, it's 3. That's why it's being updated temporarily into 3. And this alpha is something horizontally, what's the best solution for this D node. Right now it's temporarily 3. This if statement, basically it's something to make sure, do we need to check the right side of this node? This is where the pruning is happening. For this D node, he firstly checked the left child, which we got a return value 3, and then he didn't meet this if condition, so we have to check the right side, and then we check the right side, and after we check the right side, we get some return value, which is 5, and then we're gonna give this 5 all the way back to the node B, which we can shortly represent in this graph. Like for example, the D, I'm going to find the max value, which is 5, and we got a 5, and then we return this 5 to B, and now B just finished checking the left side, and now I'm going to check the right side. So we get back to B. So inside this B, we can see there, for this for loop, the I equal to 0, this situation has been executed already. For the subchild, it's all down. Now we got a return value, we get this variable, and then we can update it, the best variable and beta variable. So here we didn't meet the condition again, so we have to check the right side. So notice here, in the first for loop, when I equal to 0, our beta has been updated, since this best variable has been updated vertically, and then this beta has been initially updated. And then when we horizontally checking, when I equal to 1, we're going this way. all the way here. We're going right now, we're at this E note. Okay, so again, at this E note, we need to calling this function again, recursively calling it again, and then we're going to his subchild to take a look. First of all, from his subchild, we got a 6 from the leaf node, and then for this line, so this line we get a return value from the leaf node, which is 6, and then we're gonna update this best value. We got a 6, and also alpha, we got a 6. And notice here something interesting happened. This beta, notice this beta is something from the parent node. It's something passing from here. Okay, this it's an attribute of the node B. Okay, this is very important to understand. This is not something talking about E this node itself. This beta is something talking about the parent node, and this alpha is temporarily the best solution for this E, because we only checked the left side, we didn't check the right side. What I'm saying is, if we already met this if condition, we don't have to check the right side. If you don't believe this, you can see the right side, it only has 3 situations. Either it's going to be bigger than 6, or it's between 5 and 6, or it's smaller than 5. So if it's bigger than 6, then it's a 9. So for this E node, he's going to choose a maximum node, which is 9. And then for this B node, he's just going to choose a minimum node. He's going to choose 5 and 9. Obviously, he's going to choose 5. And also this situation, 5.5. And this E node is going to choose 6. And this node is still smaller than 6. 5 is still smaller than 6, so I'm still going to choose 5. And here, in the third situation, which is a 4, so this E node will again choose 6. And 6, again, is bigger than 5, so I'm still going to choose 5. So no matter in which of this situation, so this node is there's no need to check this node. This is where the pruning is happening. So we don't need to check the right side. We just return this 6 back to E. So here we got this return value E, and then we're gonna for this B node, we return back to B. For this B node, this is the part of program of B node. So for this part, we're gonna update the best value, which is 5, and then the beta, and again this is because this is already right node, so it doesn't matter this if statement, and then we're gonna return a 5 back to B. So let's get back to this diagram again. Firstly, we check the left side. All the way down here, we found the best value for D, which is 5. And then we return this 5 back to B, and we also set the beta for B, which is 5. And then for the node E, we firstly check the left side, the 6, and then we're comparing this 6 with the beta from the B, which 5 is smaller than 6. Then we don't need to check the right side. The reason I have already said it in the former video. And then so for this B, we just take 5 and return this 5 back to A. And for the right side, it's the same thing. So we keep continuing, execute this part. So finally, we can get our result. So the main takeaway from these algorithms is here. Every time when we're going down to a node, we're using this recursive call. So from this line, we're going to another layer, to the subchildren. And then for each of the best values, you can thinking about it as vertically the best solutions for the current node, and the alpha is horizontally the best solutions. And also, when you're comparing this beta and alpha, this beta is not talking about the current node, it's talking about his parent, the parent beta and the current alpha. So this is the main three takeaway from these algorithms. I hope you guys enjoying this video, and if you have any questions, just leave a comment down below. I will try to reply them all. Thank you. See you in the next video.